This is AP problem number 8. In aqueous solution, ammonia reacts with as represented above. In 0.0180 molarity NH3 at 25 degrees Celsius, the hydroxide ion concentration OH- is 5.6 times 10 to the negative fourth molarity. In answering the following, assume the temperature is constant at 25 degrees Celsius and the volumes are additive. Write the equilibrium constant expression for the reaction represented above. For this reaction, the equilibrium expression is NH4 plus times OH minus divided by the concentration of NH3 is equal to the equilibrium constant for the base, because the equation is NH3 plus H2O yields to NH4 plus OH minus, and you don't include H2O because it's liquid, and you know the K constant is B and not A because it results in an OH minus. Determine the pH of 0.0180 molarity of NH3. In order to solve for the pOH, you will use the equation negative log times the concentration of OH minus. You don't directly plug in the given concentration because that will only solve for your pH, and you want to solve for your pOH. So in order to solve for pOH, you set up an icebox using the equation NH3 plus H2O goes to NH4 plus OH minus. I crossed out H2O because since liquids aren't included in the equilibrium expression, you can ignore it when setting up an icebox. For the icebox, I plugged in the initial concentration that was given in the problem of 0.0180 and 0 for the others because they are not given an initial concentration. The change is minus X for any reactants plus its coefficients. So it's minus X for NH3 because it only has a coefficient of 1, and then plus X and plus X for NH4 and OH minus for the products. The equilibrium will be 0.0180 minus X for NH3, X for NH4, and X for OH minus. You then set it up in the equilibrium expression of Kb equals X squared over 0.0180 minus X, and you get X equals 5.6 times 10 to the negative fourth. Plug in your X value, and because you plug in the X value because X is equal to the concentration at equilibrium for OH minus, and you want the concentration of OH minus to solve for the pOH. So negative log times 5.6 times 10 to the negative fourth equals 3.25. That's only for your concentration of pH, so you must subtract it from 14 to get 10.75, and pH equals 10.75. And you know this is correct because in order for a basic solution, the pH must be greater than 7. So 10 is, so it indicates and matches up with the basic equation. For C, you are trying to solve for Kb, and so you must use an icebox, and you NH3 plus H2O goes to NH4 plus OH minus, and you're ignoring H2O again because it's not included in the equilibrium expression. Your initial for NH3 is 0.0180. Your change is minus X because it's a reactant with a coefficient of 1, and your equilibrium will be 0.0180 minus X. For NH4, there's no initial concentration given, so it's 0. It's a product with a coefficient of 1, so it's plus X, and that will be equal to X. For OH minus, we solved for X, which was 5.6 times 10 to the negative fourth, so that's our initial concentration. We plus X because it's a product with a coefficient of 1, so our equilibrium will be 5.6 times 10 to the negative fourth plus X. You plug it into your equilibrium expression that we had before, and you have Kb equals 5.60 times 10 to the negative fourth plus X squared over 0.0180 minus X. Plug in your X value you solved for earlier, so you get Kb equals 5.6 times 10 to the negative fourth squared over 0.01744, and therefore you get Kb equals 1.8 times 10 to the negative fifth, and since K is the equilibrium constant, there is no units. For D, you are determining the percent ionization of NH3 in 0.0180 molarity of NH3. So you plug in your X value of 5.6 times 10 to the negative fourth, and then you plug it over your 0.0180, which is your initial, times by 100, and that's equal to 3.1%.